Okay, we're going to continue on here and wrap up, hopefully, chapter 12. Right nowadays. So obviously in chapter 12, we've been talking about bonding, and last time we got into really Lewis structures. And remember that when you're drawing Lewis structures for covalent bonding, there's some steps that you do want to follow. You want to think about how it is basically put together. And you basically want, again, the least electronegative atom in the center. So again, hydrogen and fluorine should not be in the center. Again, fluorine being the most electronegative. Hydrogen should only have 2 electrons, so it should never find itself in the middle. Probably the most important thing that you want to do is count the total number of valence electrons. Remember that equals the group number. And you also need to take into account if something has a charge, you need to adjust the charge of it. The total count of electrons. So if something has a negative charge, that means it has gained electrons. So you need to add that to your total. If something has a positive charge, then it has lost electrons. So you do need to obviously subtract that from your total. Remember, we want to start with one single bond from the center out to the outside atom. So again, we want to start with just one single bond to everybody. We want to figure out how many electrons we have left, and then all those electrons go outside in as pairs of electrons. So again, if you have more electrons at that point, which you probably will, you want to fill up all the outside guys until they basically have 8, unless, of course, it's hydrogen. If you should fill up all the outside guys and you still have electrons you need to put on there, then you should go to the center, and those also should go on as pairs of electrons. At that point, once you hit the center, you should be out of electrons at that point, hopefully. The last thing you want to make sure of is that you have met the octet rule. And again, really at that point, if you have not met the octet rule, that is really where we want to maybe start with some double bonds. So again, we want to try to fix it by making a double bond. Remember that when we do make a double bond, for example, we're going to make a double bond between these guys, we're actually going to take a pair of electrons in to do that. We just don't make the double bond or add extra electrons. So again, we would bring the electrons in to do so. Or if that doesn't work, if you kind of exhausted all of your tries there with double bonds, then you would move on to triple bonds. And once again, triple bonds work the same way. If you need to make a triple bond, you're just going to bring another pair of electrons in, and you'll make your triple bond in that particular case. So we want to follow these sort of rules. It should lead you to a pretty good Lewis structure when it's all said and done. Remember, as we talked about, you don't really want a double bond or triple bond right out of the box. Again, you want to go single bond. Kind of think of double bonding and triple bonding, as we talked about, as sort of fixing a problem. You also don't want to think of, in this case with covalent bonding, that necessarily the electrons belong to anybody. You just want to kind of distribute the overall number of electrons kind of as equally as possible to everybody to get everybody to the octet rule. Any questions on any of that there? All right, so the next thing we're going to talk about is geometry, molecular geometry, and we're going to actually talk about 2 types of geometry, and they have 2 types of names. One is what is referred to sometimes as the electron pair geometry. And the electron pair geometry describes how the electron pairs are arranged around the central atom. For our purposes of this lecture, I'm just going to call that the EG, just so I don't have to write it out all the time. So if you see EG, it means the electron pair geometry. We will also talk about the actual molecular geometry as well. And sometimes people refer to that as the shape as well. And for this part of the lecture here, I'm just going to call that the MG for molecular geometry, just to sort of shorthand it. So there are actually 2 different names And in some cases, they're actually the same name depending on the compound that you're dealing with. So sometimes these names will be actually the same, and sometimes they will be different. And we'll talk about why they're different in certain cases and why they're actually the same in other cases. So let's talk a little bit about molecular geometry here. So it refers to basically the three-dimensional structure or arrangement of all the atoms in a compound. We can make a prediction based on the central atom and how many electron pairs there are around the central atom, and really how many bonds there are. So this idea, when we do geometry, it is always about the central atom. And again, you could have more than one central atom, but you always want to focus on one central atom at a time. And that is really the only thing you should look at in terms of geometry, for example, is just what's happening there on the central atom of your structure. So the basis of this approach is that we do have electrons, and obviously electrons within bonds and non-bonding electrons, they actually don't want to really be near each other because they're all negatively charged. So there is a sense of repulsion that occurs as electrons get near each other. And what ends up happening is the electrons will actually try to get as far away from each other as possible. And they cannot truly escape one another because they're bonding, but they will start to move away as far as possible. And as those electrons move, and as they're hooked up with other atoms and bonds, the overall shape of the molecule starts to move as they kind of move around to try to find a comfortable sort of situation for them to be in. Now, what we talk about here is VSEPR, and that's valence shell electron pair repulsion model. Probably why there's an abbreviation. That is a tongue twister there. And it accounts for really the geometry that we see in molecules. When we look at these type of compounds, we're going to see two types of sort of molecules. One that have no lone pairs on the central atom. So basically, in this situation, you got no dots on the central atom, so nothing going on there. And then we have one where we do have lone pair or non-bonding electrons on the central atom. So you'll at least have one lone pair or maybe two or so, but we do have dots. So to simplify, you can think of it as like no dots or dots on the central atom is sort of what's going on there. And depending on whether or not, for example, as we'll talk about, if there is non-bonding electrons involved, we may get some different geometries that occur. Now, the most important thing when you're doing geometry is kind of what we were talking about when we were talking about kind of the steric number the other day. And that is when you have a triple bond, a double bond, or a single bond, it really doesn't matter. Everybody counts in terms of electron pairs and bonds as one. So when you're doing geometry, pretty much everything counts as one. So if you have, again, a single bond, a double bond, a triple bond, they all count as one electron pair, and they also all count as one bond. So pretty much anything that you count around the central atom pretty much going to count as one, regardless, single, double, or triple. Obviously, if you have two dots, that counts as one pair of electrons as well. So again, pretty much everything's going to count as one. We basically, again, always look at the central atom when we're doing this. Now, if you draw a resonance structure, which we talked about as well last time, which again gives you multiple sort of Lewis structures that you could draw for a compound because you have multiple options as to where you could put the double bond. You could basically apply this geometry to any of the structures that you draw, and you should end up with the same geometry regardless of what resonance structure you're looking at. So let's take a look at some of this here. Let's just start with probably the simplest geometry you could have, and the simplest geometry you could have is a diatomic molecule. So in a diatomic molecule, you frankly just have two atoms, and there really is no central atom here. So the only way you can basically connect two things is a straight line. So the geometry of anything that's diatomic is linear. That is like a no-brainer. It does not matter if it is single bonded. It does not matter if it is double bonded. It does not matter if it's triple bonded. These are all be linear for the geometry. It doesn't matter if they're two different things. It will also be linear. So if you have anything that is just two things together, that's a diatomic molecule, the geometry for that is always going to be linear. And usually that's the only geometry we talk about because, again, there's not really a central atom that's happening in this case because there's only two atoms. Questions on that there? So let's get into what happens when we have more than two atoms involved. So let's take a look at beryllium chloride here. And if we draw a Lewis structure for beryllium chloride, it will look something like this. The dots on the chlorine are not put there just to keep it not so busy. This is actually an exception to the octet rule. This is an incomplete octet, and beryllium is perfectly happy. So when we go to do geometry here, this is the important one that we always want to look at, which is the guy in the center. So we always want to look at the center atom. We'll call it Ca, center atom. And these are really the two things that you want to look at. You want to look at the number of electron pairs. So in this case, it has one electron pair there and one electron pair there. That's a grand total of 2. Now, when something has 2 electron pairs, the geometry, the electron pair geometry, again, I'll abbreviate that as EG, electron pair geometry, is going to be linear. So it's going to be linear. The idea here is you have 2 electrons that don't want to be near each other. So what's going to happen is they're going to end up opposites of each other. That's as far away as possible as they could get. They basically end up in a straight line, opposites of each other, and that again keeps them as far away as possible. Now, the other thing that you want to look at is the number of bonds there are around the central atom. And there's 1 bond there and 2 bonds there. That gives me 2 bonds. So something with 2 electron pairs and 2 bonds, the molecular geometry, or the shape, that Mg, is also going to be linear. Why is that? Well, as those electrons are moving, they actually have the atoms bonded to them. So the atoms move with them exactly the same way. And they also end up basically opposites of each other in a linear geometry. A linear geometry has a bond angle of 180 degrees, which you need to know as well. So 2 electron pairs, 2 bonds. That is going to be linear and linear. Probably the best way to learn this geometry is to make a table like that, like the number of electron pairs, the number of bonds, the electron geometry, the molecular geometry, and the bond angle. And it's really the best way to sort of know or remember these is just memorization. Most people can't visualize it 3-dimensional space in their head. Electron pairs and bonds. Electron pairs are any type of electron pairs. So that could be bonding electrons or part of a bond. It could be non-bonding electron. It could be basically the dots and stuff like that. Bonds are just that. It has to be actually a bonding pair electron, an actual bond that's made. Yeah. Other questions? Okay. The next sort of geometry that you're responsible for is something like BF3. BF3 is also an incomplete octet. That's boron, which typically does that. Once again, we want to look at the central atom, which is our guy in the middle. We want the number of electron pairs. So again, in this case, we now have 1, 2, and 3 electron pairs happening. 1 pair for each bond that's there. So we got 3. Now, something with 3 electron pairs, the electron pair geometry is actually going to be something known as trigonal planar. It is sometimes also referred to as triangular. So what happens in this particular case is now we have an extra pair of electrons, and it cannot go side by side because these guys got to keep a little distance from each other. These guys want to get away from each other, and these guys also want to get away from each other. So they end up in this sort of geometry as they kind of move around to sort of maximize the distance between them and keep everybody happy. So what we want to look at now is how many bonds we got going on. So if we take a look here, in terms of bonds, we have 1, 2, and 3 bonds. So something with 3 electron pairs and 3 bonds are going to give us a molecular geometry, also trigonal planar. It is called trigonal planar because, frankly, it makes a triangle, basically, is the geometry that occurs there. Yes. The electron pair geometry describes the geometry of all the electrons that are around the central atom. The molecular geometry describes the overall shape of the molecule as a result of the types of electrons that are present. Now, in this case, as you can see, they're actually both the same. They won't always be the same. So in this case, they're the same because basically they're all bonded atoms, basically. So as those electron pairs move to get away from each other, the atoms are attached to them, so they move the exact same way. And that's why we see the same name happening for both of them, or same geometry ends up. Yeah. So this is trigonal planar. It has a bond angle of 120 degrees. And again, you do need to know the bond angle. They want you to know that here as well. So something with 3 electron pairs and 3 bonds, the molecular geometry is trigonal planar. The electron pair geometry is also trigonal planar in this case. The next type of geometry is one we see like in methane. So when we look at methane, once again, we're going to go to our center atom. We're going to count up our electron pairs around the central atom. 1, 2, 3, and 4. Something with 4 electron pairs gives an electron pair geometry of tetrahedral. And this also is the same idea. We now have an extra pair of electrons there. So they cannot get as far away from one another. So they're going to have to kind of keep a little bit more distance. In terms of the bonds, we have 1 bond, 2 bonds, 3 bonds, and 4 bonds. And that will give us 4 electron pairs and 4 bonds. The molecular geometry here is also going to be tetrahedral. Older books and people will sometimes also call it tetrahedron, which is kind of the same thing. The bond angle here is 109.5 degrees. It kind of makes a triangle on the face and almost like a pyramidal type of situation on the bottom that's kind of happening in that situation. So electron pair geometry tetrahedral for 4 electron pairs. Molecular geometry tetrahedral for 4 electron pairs and 4 bonds. Now, up until this point, as you can see, both the electron pair geometry name and the molecular geometry name for all the ones that we've done so far are exactly the same. And the reason they're exactly the same is there is no non-bonding electrons here. So you have no dots on the central atom. No dots are lone pairs. And all you have are bonded atoms, are bonded electrons. And what that means, as I was just saying a second ago, as those electron pairs move, so are those bonded atoms. And they will end up in the same geometry. And what we will see is the name will actually start to change once we incorporate non-bonding electrons around the central atom. So once we get dots around the central atom, which are the non-bonding electrons, the actual overall molecular geometry will change. So what we're going to see now is it's actually the molecular geometry name will change. The electron geometry name will still be the same. So regardless of how many bonds and stuff that you have. The electron geometry is still based on how many electron pairs you have. So why does the name change? Why do we get some different shapes? It's because we're adding into the mix lone pairs, our non-bonding electrons. And there is a level of I'm okay being near you, and to I'm not so great being near you. I really don't want to be near you at all. And there is a repulsion type force that occurs. The best situation is sort of what we were just looking at, where you have bonding electrons near bonding electrons. So basically where you have lines near lines. That's all good. You know, they could be happy with it. The next best situation, which is getting a little worse, is when you got like lines or bonds near non-bonding electrons. They really don't want to be near each other. And probably the worst situation is when you have non-bonding electrons near non-bonding electrons, dots near dots. They want to move away from each other. The reason that we get different geometries over here in this situation is because they do not have atoms there, which gives them a little bit more freedom. As they move out, they could kind of get further away. And as those non-bonding electrons move, they're able to change the shape of the molecule a little bit. So because of those non-bonding electrons and the repulsion forces, they're going to try, like I said, to try to get away as far as possible from each other. So let's see how this sort of works. We'll take a look at SO2. And if we draw SO2's Lewis structure, which we might have did the other day, and again, I'm not going to draw the electrons on the oxygen here. We're just going to focus on the central atom once again. And in this case, we want to do the same thing. We want to count the electron pairs. So when I count the electron pairs in this particular case, I have one electron pair, I have two electron pairs, and remember that when we're doing geometry, double bonds count as one electron pair. So ultimately, I will have now 3 electron pairs. So the 3 things that I circled would give me my 3 electron pairs. As I mentioned a second ago, the electron geometry does not change. So as we saw earlier, 3 electron pairs is trigonal planar in terms of the electron pair geometry. But what happens in this case is these non-bonding electrons and bonding electrons do not want to be near each other. So they're going to basically get away as far as possible from each other, and they're going to kind of go upwards. And as they go upwards, the oxygen guys are going to try to go down. Remember, these guys also can't get too close to each other because they don't want to be near each other either. So it ends up giving this sort of shape here as we look at it instead of sort of that trigonal planar shape. And that's because in this case, in terms of the bonds, we actually have only one bond there for a double bond and 2 bonds. So that is the number of bonds that we have. So something with 3 electron pairs and 2 bonds will actually end up with a molecular geometry. I'm going to go with angular. I will say that some people will call this bent or bent angular, but we're going to go with angular in this class for a particular reason. And again, they're able to do this and stretch out a little bit more because there is not that extra bond that we see there in the trigonal planar situation. And the bond angle here is approximately less than 120 degrees. So the bond angle here is less than 120 degrees. It is based off a trigonal planar, but we have one less bond, so it will actually be a little bit less than 120 degrees. Bless you. All right, so the next geometry here that we have some non-bonding electrons is ammonia. So if we take a look at the central atom, we're going to count up our electron pairs. We have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So again, here you can see it doesn't matter if they're dots. It doesn't matter if they're lines. It doesn't matter if they're double bonds, triple bonds. We count everybody as 1 electron pair. That is basically what we do, what we talked about with the steric number. So again, that is how you calculate that steric number. In this case, that is 4. We know from previously that something with 4 electron pairs. In terms of the electron pair geometry, is going to be our tetrahedral situation. In terms of our bonds, we have 1, 2, and 3 bonds. And what's going to happen in this situation is kind of a similar deal. You're going to have those non-bonding electrons trying to get away. That's going to force those hydrogens this way. But again, each of these hydrogens kind of need to keep some distance with those electrons and keep the maximum distance here. And we end up with a geometry, a molecular geometry known as trigonal pyramid, or pyramidal, is sometimes referred to. And that has a bond angle of less than 109.5 degrees. So about 107 in this case for this guy. It is trigonal pyramid because it kind of makes a triangle, and then you got that pyramidal shape happening there as you go through it. This is also a good point to talk about the two names that sound similar. Earlier we saw trigonal planar, and here we have trigonal pyramid. They are different, yes? So you need to specify which one it is. You cannot just write trigonal unless you would like an X, yes? You cannot just do my other favorite when people write, they're very confident on the first one, that's like trigonal, and then it's like pyramid, you could clearly see planar or pyramid written there, yes? So don't let me choose, because I'm going to choose wrong, yeah? So you choose correctly the right one, and again, they are different. They are different bond angles. They are different geometries as well. So just don't write trigonal. Got to write trigonal planar or trigonal pyramid, depending on which one you're doing. Any questions on that? Yeah. Yeah. I would say probably in this situation for this stuff, the best way is just memorization of it, to be truthfully honest with you. We go with less than 109.5 because, again, things that have this sort of geometry will vary between, like I said, this is probably like 107 or something like that degrees or something like that. So there'll be some variance depending on what molecule you're drawing. So I would say you just should remember the bond angles based on, and it is based on the electron pair geometry. So if you remember it for the ones that have no non-bonding electrons, all you have to remember is when you got the dots, it's just going to be less than that number, basically. Yeah. So if you looked at the one we did for 3 and 3, I'm sorry, 4 and 4, it said the bond angle was 109.5. This one is 4 electron pairs, but with dots, so it's just going to be less than that number. Yeah. The next geometry, I'm not sure where that slide went, but we should probably talk about the next one. That's probably important. Is water. Let's take a look at water here. If we draw the Lewis structure for water, not sure where that slide went. All right. We draw a Lewis structure here for water. It looks something like this. And again, we're going to want to look at the central atom. And we want the number of electron pairs. And again, we don't care what they are, dots, double bonds, triple bonds, single bonds, 1, 2, 3, and 4. And number of bonds in this case, 1 and 2 only in terms of bonds. So once again, the electron geometry, it has 4 electron pairs. So this also is going to be tetrahedral. But because we have 2 bonds here, and really because we have 2 non-bonding electrons, water has all the worst interactions happening together. It has bonding electrons near bonding. It has non-bonding electrons near bonding. And it has non-bonding electrons near non-bonding electrons, which is like the worst case scenario. So what's going to happen in this case is those non-bonding electrons are basically, if these are them, they're going to try to get as far away as possible. Once again, though, there are some bonding electrons there with hydrogen, which also needs to keep their distance between them. And obviously these hydrogens got to keep their distance between them. So what ends up happening is the molecular geometry, because of that non-bonding electron repulsion, is we're going to end up with what is known as bent or V-shaped. And that is why you always typically will see water a lot of times drawn like this. Bent or like a upside down V type of shape is why they do that. And this has a bond angle based off of our electron pair geometry of less than 109.5 degrees. Again, this is like 104-ish in that ballpark in case of water. This is why as well that we are going to use angular for like the SO2 example there, because the bond angle is closer to 120 degrees versus this bent or V-shaped, which is closer to 109. Yeah. Yeah, so this is why we will pretty much in this class use angular for this. And this is because this actually only has 3 electron pairs, right? So it has actually only one non-bonding electron happening. And that will make it actually less than 120 degrees. Versus this one here where they're going to have these 2 non-bonding electrons, it's actually going to spread it out a little bit more because of that. And it's going to cause it really a different bond angle, a much sort of lower bond angle because of that. And there is really a difference between the bond angle in both of those. And that's why a lot of people use angular, but nowadays in books, people will still use bent for that. So you will definitely in books and people will still use bent. Sometimes people will use bent angular to distinguish it that it's more the 120 sort of degrees versus the bent or V-shaped here for that one. So for us in here, we're going to roll with this for the previous one because it is slightly different on the bond angle and how many electron pairs there are. And then we'll use this for our 4 sort of and 2 relationship that has there. But again, don't be surprised if online or in books and stuff, they do use bent for kind of the SO2 there, like the 3 electron pairs and 2 bonds as well. Yeah. Any questions on that there? So like I said, probably the best way to do this is to make a table, kind of like what we did, number of electron pairs, number of bonds, and again, the electron pair geometry name and the molecular geometry name that goes with it and the bond angle. And here's one from your book. And again, it pretty much does that. That again is our number of electron pairs. That's our number of bonds, our electron pair geometry, and our molecular geometry. As we saw there at the end, once we get into those non-bonding electrons being involved, the molecular geometry name will change, yeah, but the electron pair geometry name will be the same. Any questions on that there? So then let's talk a little bit about, some of the ones that we maybe drew before. So just to quickly go over a couple of those that we did previously, I think had some of that. All right, we had something that looked like that, I think. And I think we actually did this guy, right? So here's what we want to look at, right, when we take a look at this. Here, actually, I think we did this guy too. We'll do this one. So if we want to do our geometries here, we would look at our central atom. We would look at, again, electron pairs. We have 1 and 2 for our double bond, 1 in for each. In terms of bonds, 1 and 2. So again, the electron geometry name here will be linear, as it's 2 electron pairs, and 2 bonds means the molecular geometry name here will also be linear. Again, no dots on the central atom. Both names are the same. We come over here, right? We take a look at our nitrogen. It has 1, 2, 3, 4 electron pairs. It has 1, 2, 3, 4 bonds. Once again, something with 4 electron pairs, the electron geometry going to be tetrahedral. with 4 electron pairs and no dots on the central atom, the molecular geometry will be, again, the same name. We come over here to our CO3 2-, take a look at the central atom, electron pairs, again, 1 for the double bond, 2 and 3 total. In terms of bonds, 1 for the double bond, 2 and 3. 3 electron pairs is our electron geometry of trigonal planar. Again, no non-bonding electrons there, so our molecular geometry also going to be trigonal planar. We come down here to our SH2 that we drew. Again, looking at the central atom. Electron pairs in this case, 1, 2, 3, and 4. Again, when you're counting electron pairs, doesn't matter if they're dots or lines. You're just counting everybody as 1, basically, yeah? So we got 4. Bonds, though, that is important. That has to be just the lines or bonding electrons. So that's 1 and 2 in this case only. So once again here, with 4 electron pairs, the electron pair geometry is tetrahedral. With 2 bonds, that's going to get us to our molecular geometry we saw at the end there. That's going to be our bent or V-shaped in this case, yeah? Question on any of those there? No? By the way, when I have 2, the geometry here is, yeah, just linear, yeah? Bond angle, right, for my first guy up here, it is based off of this. No dots, it's 180 degrees. Over here, it is based off of tetrahedral, no dots. It's going to be 109.5 degrees. Over here, it is based off trigonal planar, no dots on the central atom, going to be 120 degrees. Over here, based off of tetrahedral, but I have dots, right? So that's going to be less than my normal, 109.5 degrees. And over here, you really don't have to worry about bond angle because there's no central atom, basically. Any questions on geometry or how to apply it correctly? Okay, then the last thing we're going to talk about is what I just scribbled all over this thing, huh? Last thing we're going to talk about is molecular geometry. And molecular geometry, I'm sorry, not molecular geometry, molecular polarity. I'll spit that out, right? So we're going to talk about molecular polarity. And that is what dipole moment means. When we're talking about molecular polarity, we're talking about the entire molecule. So molecular polarity is dealing with the entire molecule. And that is slightly different than bond polarity that we did earlier when we did the difference in electronegativity values. So that is a little bit different in some cases. If you have a polar molecule overall, and what that means is overall in the entire molecule, they are not sharing electrons equally, you will have a dipole moment. Dipole moments are represented by the same arrow we used when we did bond dipoles. This points to the more negative side of the molecule. This points to the more positive side of the molecule. Nonpolar molecules are pretty much neutral. They are going to share the electrons equally over the entire molecule, which means there is no dipole moment in those cases. So only polar molecules will have these overall dipole moments. Nonpolar molecules will not. So let's just start with pretty much the simplest ones that you could have. And the simplest sort of molecular polarity type problems you could have are diatomic molecules. And diatomic molecules, the molecular polarity and the bond polarity, like when you do difference in electronegativity values, they're actually going to be the same. So what I mean by that, for example, if you had hydrogen, we know that if we took the difference in electronegativity here, right, we're going to hit a 0, which means that that bond is nonpolar, right? So that bond is a nonpolar bond. Now, the deal with this is how many bonds are there in this molecule? Just one, and that one bond is nonpolar, which means the molecule itself will also be a nonpolar molecule. And that is because the only bond present is nonpolar, so the whole thing's got to be nonpolar in this case. Same thing if you had a triple bond like nitrogen. That is a nonpolar bond. Difference in electronegativity would be 0. Nonpolar bond. And that would mean that that is the only bond present. That would be a nonpolar molecule. Now, the opposite is true if you have a heteronuclear molecule. That's something like HF. When we look at HF, the difference in electronegativity, right, is like 1.9, I think, something like that. That is a polar bond, right? So that bond is polar. Much like the other one, there is only one bond in there, and it's polar, which means that this guy would have to be a polar molecule. And we could draw our dipole moment in this case heading towards the fluorine. It would be our dipole moment basically heading in that direction. So if you have a diatomic molecule, they are the simplest to decide, is it a polar molecule? Is it a nonpolar molecule? And basically, if the bond is nonpolar, the molecule will be nonpolar. And if the bond is polar, based on electronegativity difference, the molecule will be a polar molecule. So they are like the simplest ones possible because there's just one bond, and whatever that bond is in terms of polarity will be what the molecule is in terms of polarity. Same thing if you had something like HCl. That is a polar bond. That is also going to be a polar molecule that has a dipole moment heading towards the chlorine in this particular case. Question on molecular polarity of diatomic things. Yeah. Now, that would be wonderful if you could do that all the time, but you can't. So when you get to 3 or more atoms, you have to actually look at 2 things. You have to look at, are there polar bonds? And if there are polar bonds, you have to look at the molecular geometry. And that was the MG we were doing a second ago. So let's just take the classic example of carbon dioxide. When we look at carbon dioxide, does it have polar bonds? Is the bond between carbon and oxygen polar? The answer is yes. Carbon and oxygen is in the same row on the periodic table. Oxygen is further to the right. So it does have polar bonds heading in this direction. So yes, it has polar bonds. Now you may think that this is a polar molecule, but we just did the geometry of this a second ago. The molecular geometry of this is 2 electron pairs and 2 bonds. The molecular geometry of this is linear. It is basically a straight line, which means if I have my CO2 molecule, which is my pen, and on one side I have the oxygen pulling this way, and on the other side I have the oxygen pulling the other way, I'm actually pulling really hard. Is my pen going anywhere? It is not. So even though it has polar bonds, because of the geometry, they actually cancel each other out. And this is what is known as a nonpolar molecule. So it is possible to have a molecule that has polar bonds, but because of the geometry, they actually cancel each other out. Now, if you take something like water, for example, water also has polar bonds heading towards the oxygen in this case. Now, what happens in this case is it is geometry, as we just saw, is bent or V-shaped. So if you think of sort of water like this, you kind of have everybody pushing this way, everybody pushing this way, kind of meeting on top, almost like if you had a string up on top and you kind of just pulled it, you could kind of imagine that the whole thing would kind of move. And because of that, it gets what's known as a net dipole moment heading in that direction, and this is a polar molecule where the oxygen is more negative, the hydrogen part of the molecule is more positive. That is because these are vectors, these bond dipoles. They have direction, they have magnitude, and I fell asleep in physics after that, but I think in some cases they add to each other. In other cases, they cancel. By the way, how that works, by the way, is like, You draw the vector arrow that way, you go head to tail, and then you connect the dots basically, right? And that's how we get the bond pole going that way. So to end up with really quickly here, which is nobody really wants to do vectors or figure that stuff out. So there is a really quick way that you could do it. And the quick way you could do it is there are certain geometries that are symmetrical geometries. And those are all the geometries where you have no non-bonding electrons on the central atom and everybody outside is the same. It will actually be a non-polar molecule. Everybody will cancel. If you draw a Lewis structure and you have dots on the central atom, and everybody on the outside is the same, it will most likely be a polar molecule. So you can kind of do that pretty quickly. All right, let's talk about a couple